Hey everybody, welcome back. We are starting chapter 4. Chapter 4 is on atoms and elements, and because it's kind of a long chapter, I'll be breaking it up into 2 videos. So make sure that you watch them in order. This is part 1. Watch part 2. You need them both. We'll start with the elements and symbols. Remember from chapter 3 that we talked about elements, and elements are pure substances. Everything around you is built from elements. You can't break elements down into anything simpler, at least not by chemical means. And the elements are listed on the inside front cover of your textbook. They're also listed in the periodic table, any periodic table that you would find on the internet. We're going to talk about the names of elements, their symbols, and things of that nature. The names of elements come from a wide variety of places, from planets to mythological features or figures, colors, locations where they were first found, people who discovered them, all sorts of places. Chemical symbols represent the name of the element, and that's what you're going to see on the periodic table. They'll either have 1 or 2 letters and always start with a capital letter. Some examples of 1-letter symbols are C for carbon, N for nitrogen. 2-letter symbols, some examples are cobalt, that's a capital C with a lowercase o, and calcium with a capital C and a lowercase a. There are a couple of learning checks that I'm not going to go through all of them. I'm pretty sure that if you've gotten to college, that you have encountered the periodic table and that you can, using a periodic table, write down the correct chemical symbol for each of these elements. But just in case, I'll go through and do a couple of them, and you make sure that you can do that yourself. So you would find iodine on the periodic table. Its symbol is an I. You'd find the word iron, and its symbol is Fe. So you'd go through and do that for each of these. If you have trouble, please let me know. If you've never seen a periodic table before, if it is completely foreign to you, or you're just anxious about the course in general, and so all of the knowledge that you had completely out the window, it's fine. Let me know. That's what I'm here for. You should also be able to do the opposite. If I give you the symbol, you should use the periodic table to look up the name. I'll write a couple of these out, but again, this is just making sure that you're familiar with the periodic table and how to read it. If you find the P, you'll see that that's for phosphorus. Al is aluminum. Go through these, make sure you can do them. Even if you don't do it in your notebook, make sure that you have a periodic table and you kind of glance at it and say, okay, yeah, I can do that. If you can do that, you're good to go. Now we'll look at the periodic table in a little bit more detail. We started looking at it in chapter 3. We talked about metals and nonmetals and where they are on the periodic table. We brought up the term atomic number, but we didn't really go into depth. Now we are. We're going to learn how the periodic table is organized and some of the different properties that are also organized based on the organization of the periodic table. So, the elements are arranged according to their properties. We'll talk a little bit more about why and how later on. There are groups and there are periods. The groups contain elements with similar properties in vertical columns. Remember that vertical, that means up and down. Periods are the horizontal rows of elements, and you count them from the top of the table to the bottom of the table, 1 through 7. The way that I remember the difference is this little mnemonic. I write group and period. Groups are up and down, the vertical columns. The periods are left to right, horizontal rows. This is a periodic table. There's a lot of information here. We're going to go through and talk about a lot of these different pieces of information you can glean from the periodic table. The first I want to draw your attention to is the different colors. We've got metals, metalloids, and nonmetals, and we'll talk more about what those really are. You also have the small number at the top above each symbol. That is the atomic number. I want to draw your attention to the groups. There's these numbers with the B or the A after them. Pay attention to those. We'll be coming back to them later on. We also have periods. I'll highlight those in green. Every periodic table will not have the periods numbered, but the groups will absolutely be numbered. We've got two kind of distinct groups in the main portion of the periodic table: the representative elements and the transition elements. We'll talk about what those are as well. And finally, we've got some common names. So that's all the stuff we're going to address. That's just the basic outline. But you see this small little table? All that information. We'll start with the group names. All of the groups do not have names, but the ones that do, you're responsible for. As I said, the group numbers are written at the top of each column. The letter A is used for the representative elements, and the letter B is for the transition elements. There's an alternative system that just numbers them 1 through 18, but it's not as helpful when it comes to identifying some of the different periodic trends we'll talk about. Alkali metals. This is group 1A. All of the alkali metals are listed here. These metals are very, very reactive. If you put any of these metals in water, there will be a very, very, very violent reaction. Lots of gas formation and just a lot going on. You can look it up on YouTube. It's kind of cool. Then we have the alkaline earth metals. These are also reactive, but not as reactive as group 1A. You'll see that these are listed here as well, the group 2A metals. Some of these are actually used in fireworks. We're skipping over quite a bit of the periodic table and going to group 7A, which is on the right-hand side. 7A, those are the halogens. They're also highly reactive, and they will form a compound with most of the elements on the periodic table. The halogens that we're talking about specifically are listed here: fluorine, chlorine, bromine, and iodine. Now let's talk about metals, nonmetals, and metalloids. There's a zigzag line that is more distinct on some periodic tables than others. In your book, It's very distinct. That zigzag line separates the metals and the nonmetals. So the metals are to the left. The nonmetals are on the right. And on your periodic table, those metals are kind of like a periwinkle blue. And the nonmetals are yellow. The metalloids are along that zigzag line, and they're green. In a second, you'll see why they're kind of sandwiched in between the metals and the nonmetals. The characteristics of metals and nonmetals. All the metals except for hydrogen are located on the left-hand side of the periodic table. And you'll need to know the characteristics. They're shiny, ductile. Think about a metal. Think about a coin, or if you have jewelry, anything that's made of metal. It's shiny. Metals can be extruded into long wires, and that's what ductile means. You can hammer them, you can extrude them into thin wires, and they won't break. Metals are also conductive. They're great for conducting heat and electricity. And for the most part, they're solids. There is an exception. Mercury is a liquid at room temperature. Mercury is kind of weird. It's also something you don't want to touch. Thermometers used to have mercury in them. They don't anymore. They usually have alcohol in them now. But that aside, metals are usually solid. So you're responsible to know all of the characteristics of metals. And these are general, so there are going to be some exceptions here and there. Nonmetals, which remember are on the right side of the periodic table, are dull, they're brittle, they're terrible conductors, and they have low densities and low melting points. Nonmetals are essentially the exact opposite of metals. So if a metal is shiny, then a nonmetal is dull. Metals are ductile, you can work them with a hammer. Nonmetals, they're brittle. You try to hammer them out, they'll break. They're poor conductors, whereas metals are good conductors. So if you can memorize one set of characteristics, then you can know that nonmetals are the opposite. Metalloids, which are the ones along that zigzag line, and they were green on your periodic table. They have a combination of properties from metals and nonmetals. Some of them are better conductors than nonmetals, but not quite as good as straight up metals. So they have a mixture of properties. There is no list of what a semi-metal is in terms of properties. So just know it's a combination. Metalloids, I sometimes say semi-metals. They're the same thing, just different terminology. This chart will help you a lot, and I'd recommend just having this chart in your notebook. If you can print it out, print it out. If you are the type that likes to write things down, copy this chart into your notebook. It'll be great when you're doing your homework, because you can have solid examples, not just what the characteristics are, but how you can talk about these characteristics. So we're talking about all of the elements. We're people. That means that we are matter. We have mass, so we're matter. We're made up of elements. And there are 20 essential elements for the well-being and survival of human beings. We absolutely need oxygen, carbon, hydrogen, and nitrogen. That's the majority of our body mass right there. Most of our hydrogen and oxygen is found in water, and we're mostly water. There are also some macro minerals that we require. So if you think about all the, commercials and things you see, like for cereal, breakfast cereal is like, we've got this many essential minerals and vitamins. They're talking about with the minerals, calcium, potassium, magnesium. All of these are macrominerals that are required for formation of bones and teeth, maintaining heart and blood vessels. So that's going to be like the salt and potassium. They're involved in a lot of that. Muscle contraction, nerve impulses, acid-base balance of your body fluids, which we'll talk about that more when we get to chapters 9 and 11. And a lot of these macrominerals have a lot to do with regulating your cellular metabolism. So all of the chemical reactions that are going on in your body to keep you going, they're regulated by these minerals. So the major elements of the body are circled, or I guess they're squared. I'll make that a word. They're squared. They're highlighted in red. Then you have the macrominerals in blue, and the microminerals, which are things that we need very, very small amounts of, in purple. So an example of that would be iron. There's iron in your blood. If you don't have enough iron, you're considered anemic, which can be a problem. But you don't need a ton, but you need enough so that your red blood cells can actually hold on to oxygen and transport it, which is the job of a red blood cell. There's also zinc. Zinc is used in a lot of enzymes, which enzymes are just proteins that do chemistry. And sometimes they need helpers. And those helpers come in the form of microminerals or what's called cofactors. Either way, these elements are essential to our health. So what have we covered so far? We've talked about the periodic table, the elements, their symbols, a little bit about the organization of the periodic table. But now we need to take an even deeper dive and look at what an atom is. So we'll start by kind of the structure of the atom. Then we'll also get into a little bit of the history of how the atomic structure we know today came to be. So it'll be a little bit of a history lesson too. We'll start with Dalton's atomic theory. So John Dalton, he did a lot of work with biology in addition to physics. And so his theory has 5 postulates or 5 points. Atoms are tiny particles of matter. Atoms of an element are similar to each other and different from those of other elements. So if I have 2 atoms of aluminum, they're similar. But if I have an aluminum atom versus a gold atom, those are different. I'll write that down. Au is the symbol for gold. So 2 aluminum atoms, they'll be similar. An aluminum atom and a gold atom, they'll be different. Atoms of 2 or more different elements combine to form compounds. So let's say that you had H2O. That's 2 different elements coming together and forming a compound. We lovingly call it water. Atoms can be rearranged to form new combinations in a chemical reaction. So if you do some chemistry, you can make H2O2, which is hydrogen peroxide. Still only has hydrogen and oxygen, but now it's something totally different because there's a new ratio of hydrogen atoms to oxygen atoms. Atoms are never created or destroyed during a chemical reaction. What is the atom made of? The atom contains subatomic particles. The types that we'll talk about are the protons, electrons, and neutrons. And you've likely heard of these already. So if this is a review, you're in a good place. The protons have a positive charge, and I'll do a little bit of highlighting here. So protons, positive. Electrons, negative. Neutrons are neutral. Okay, that means they have no charge. Like charges will repel each other, and unlike charges will attract. So just remember, opposites attract. That means a positive or proton and a negative will be attracted to one another. But if you have two protons or two electrons, they will repel each other and try to get as far away from each other as possible. Now let's talk about some of the other theories of what the atom looked like. We're going to build some history here. There's a man named J.J. Thomson who did work with cathode rays. And he realized that these cathode rays contain negatively charged particles. We now call them electrons, and they have a really teeny tiny mass. He also proposed a plum pudding model of the atom, where the protons and electrons are just kind of randomly distributed in this positively charged cloud, like plums in a pudding. Now, J.J. Thomson, not exactly from the U.S. Plums, what they really mean are raisins. So it's like raisins in a pudding. And the raisins in the analogy are electrons. What does that look like? So you have this positive pudding, this sea of charge. And dotted throughout are the negative electrons, or the plums. So that was his model of the atom. And this sea of positive charge was just a lot of empty space. And then you had some electrons kind of dotted around in there. However, Ernest Rutherford, who was a student of J.J. Thomson's at one time, he, matriculated, got his own lab, started doing some work. And he had a graduate student that was working with/for him, and they came up with this gold foil experiment. This experiment is what led to kind of a really big breakthrough in terms of how we understand the atom. What Rutherford set out to do was test the plum pudding model. So he said, okay, Thomson, it was great working with you. I see this theory that you have developed, which I'm sure I have helped you with tremendously, but no one mentions that. I'm now going to go off to my own lab and do some work with my own graduate student, and then only have my name put on the slides. And what I'm going to do is test your theory. If the plum pudding model is correct, then I should be able to shoot particles at thin gold foil, which is just gold atoms, right? And all of those particles should just go straight through. And that would be evidence that the plum pudding model is correct, because the plum pudding model says there's just empty space in these teeny tiny little electrons. So that's what he did. He set up a source of particles, alpha particles to be exact, and he sent that beam through a thin foil of gold. There was a fluorescent screen for them to detect where the particles would hit. So if they went straight through the foil, then you can detect where it is. If it got scattered, then you would detect it somewhere else. They didn't expect to see deflected particles, but they did. So most of them went straight through. Most of the large particles went straight through. But there were some deflections. And the deflection said, well, there must be something massive enough to make these large particles change direction. So Rutherford concluded there must be a small, dense, positively charged nucleus that's deflecting those big particles that he was shooting at them, and it's likely in the center. So some sort of dense positive center. We know that now as the nucleus. And the nucleus, which is the center of the atom, contains the protons and neutrons and represent the majority of the mass of an atom. The electrons, they occupy a large empty space around the nucleus. Remember, the electrons are so teeny tiny that it's pretty much empty space around that nucleus. This is just a depiction. So if you look at the metal, right, something that you could touch with your hand, well, I wouldn't recommend it, but you can use some tweezers or something. Lithium is one of those group 1A metals that's very reactive, so you don't want to have it just in open air. Well, that piece of metal is made of lots and lots and lots of lithium atoms. And if you could see one individual atom, what you would see is all this empty space with these teeny tiny little electrons and a nucleus in the center. That nucleus, if you could again look at it with your eye, you would see that it's a cluster of neutrons and protons. Since all of these subatomic particles are so small, what we use is called the atomic mass unit when we're talking about the mass of these particles. 1 AMU, which is the abbreviation, has a mass of 1/12 the mass of a carbon-12 atom, which has 6 protons and 6 neutrons. 1 atomic mass unit is the same as 1 Dalton in biology. So if you're talking about how much the mass of a protein, you'll likely see Daltons, not atomic mass units. And the electrons are so small and they have such a small mass that they're usually not even included in the mass of an atom. So that gives you an idea of just how small they are in comparison to protons and neutrons. Here's a table that summarizes the symbol, charge, mass, and location of each of the subatomic particles that we just went over. This is another good chart to put in your notebook. Make sure that you recognize these symbols. I'll be using them throughout this lecture and in class, and you'll see it in your homework. Moving right along, now that we have some history under our belt about the structure of the atom and a little bit of how we got there, now we can talk more about the atomic number, the mass number, and some other properties of elements. The atomic number is a whole number, and it is specific for each element. So each element has its own unique atomic number. It's the same for all atoms of a particular element. So if I have an atom of sodium here in North Carolina, if I find an atom in South Carolina or in Georgia or in Tennessee, it too will have the same atomic number. That atomic number on the periodic table is usually listed above the symbol. So it is a whole number above the symbol. And sodium's atomic number is 11. The reason we care about the atomic number is because that tells us how many protons are in the atom. That'll be really good for us when we're doing some of our radionuclear chemistry later on. So please make sure you know this. So the atomic number tells you the number of protons. If you look at this blow up of all these elements, notice that we're going in increasing number order of atomic number. All of them are whole numbers, and it tells you how many protons you have in a given element. Make sure that you can recognize the atomic number. I know it seems really simple, but once we start looking at a periodic table that has more numbers than just the atomic number, sometimes students have a tendency to switch the two. They'll switch around the identity of the numbers, and then you're like, no. So make sure you know the atomic number is a whole number. It's the number of protons. Said that enough? Let's move on. This is just showing you an example of what that atomic number means. When you have an atomic number of 3, let's say, in lithium, it means that you've got 3 protons, which our protons are in red, and you have at least 3 neutrons. I'll explain that in a minute. And you also, in a neutral atom, will have 3 electrons. For neutral atoms, the net charge is 0. Remember that we've got positive protons and negative electrons. In order for an atom to be neutral, the number of protons has to equal the number of electrons. If aluminum has 13 protons and 13 electrons, the net or the overall charge is 0 because you're taking a positive 13 from the protons. And remember, we can call that a P with a plus sign. And our charge from the electrons is negative 13. And if we total that up, it equals 0. So I rewrote it so that you can see it a little bit differently. That it's just math. Positive 13 plus a negative 13 gives you 0. So remember that for neutral atoms. Let's use the periodic table to fill in the atomic number, the number of protons, and the number of electrons for each of these. What you'll want to do is look up each of these elements using their symbol. N is nitrogen. Its atomic number is 7. That means that it's got 7 protons and 7 electrons in a neutral atom. Now, I'm not going to go through and fill in all of these. You can fill these in on your own time just to make sure that 1, you can locate the atomic number. 2, you can write out the name of the element from the symbol. And 3, that you understand the number of protons and electrons and how they're related. In addition to the atomic number, there's also a mass number. The mass number is not listed on the periodic table. It represents the total number of particles in the nucleus. And remember that that means we've got a total of protons plus the number of neutrons. That's the total number of particles in the nucleus. It's always a whole number. You're not going to have half a proton. You're not going to have 0.3 neutrons. Always a whole number. And as I said, the mass of a single atom does not appear on the periodic table. So that mass number, you will not see it. This table has the composition of some atoms of different elements. If you learn by example or you like to see how it all is laid out together, this table will be great for you to look at and kind of talk yourself through. So let's say we're talking about hydrogen. Its symbol is H. The atomic number, which is the number above it, is a 1. The mass number for hydrogen is also 1. It has 1 proton, no neutrons, and 1 electron. Let's skip down to oxygen. A neutral atom of oxygen has an atomic number of 8 and a mass number of 16. What that means is you've got 8 protons and 8 neutrons. That's the 8 plus 8. It gives you 16. There are also 8 electrons in a neutral atom of oxygen. So if you take these two columns and you add the two numbers, it equals the mass number. It's just another visual for you to see that. So here's a little summary. We've got the number of protons, that's the atomic number. Protons plus neutrons, mass number. If you need to figure out how many neutrons you have, then you take the mass number and subtract the atomic number, which is the number of protons. Mass numbers are given for specific isotopes. So you'll be given that information, or you'll at least be able to figure it out. Let's do a learning check. An atom of lead has a mass number of 207. And remember, we're always talking about neutral atoms here. We'll get into a space where we're talking about ions, but we're not ready for that yet. Neutral atom of lead, mass number of 207. You'll need a periodic table here. How many protons are in the nucleus? You'll need to look up the atomic number. And that's why I said you need a periodic table. It's 82. If we want to figure out how many neutrons there are in the nucleus, and we're looking at this specific isotope, then you would take the mass number, 207, and subtract the number of protons. That will give you the number of neutrons. How many electrons are in the atom? Well, we know that in a neutral atom, protons equals electrons. So the number of protons we have, same number of electrons. That means we have 82 electrons. Because our protons, that's the atomic number. We'll do more of these in class. Make sure that you can answer questions like this. Figure out if I gave you the number of protons, neutrons, and electrons, you should be able to figure out the mass number. You should be able to say what the atomic number is. So know how all of these things are related. Now we're getting to isotopes. So we alluded to isotopes talking about mass numbers and how, well, we're not going to give you the mass number for a single atom on the periodic table because, well, it's an isotope. There are many different isotopes, and we can't put all of that information on the periodic table. It would be huge. But we do need to have some way of writing out isotopes and talking about them. So isotopes are atoms of the same element with different mass numbers. They have the same number of protons, but a different number of neutrons. When you write their atomic symbol, you can distinguish among them. So right here we have the atomic symbol for magnesium, which is Mg. To write an atomic symbol, you have to have first the symbol of the element, and then you write the mass number as a superscript on the left top part and the atomic number underneath that. Remember, the mass number is the protons plus the neutrons, and the atomic number is just the protons. Magnesium has 3 naturally occurring isotopes, and it has an atomic mass of 24.31 atomic mass units. That's this number here. So every periodic table will have 2 numbers. The top whole number is the atomic number, and the number underneath with the decimal is the atomic mass. If I wanted to write the isotopes of magnesium using atomic symbols, well, we already know Mg 2412, but we also have an isotope with 25 as a mass number. If I wanted to figure out how many neutrons this isotope had, I would take 25 and subtract 12, and that would equal 13. The most abundant isotope, magnesium 24, it has 12 neutrons. There's also magnesium 26. It has 14 neutrons. The other way that you can write these isotopes is by writing out the name of the element followed by a dash and the mass number. You can also do it with the symbol. So those are all different ways of writing different isotopes. This table just does the same thing that we were doing on the last slide. We've got the atomic symbols, the names, and then you can go through and write the protons, electrons, mass number, and calculate, like we did, the number of neutrons. The mass of each isotope is listed, and that's the decimal number in atomic mass units. Then we've got this percent abundance. What that means is, well, there's a lot of magnesium in the world, but how much of it is magnesium 24? How much of it is magnesium 25? And how much is magnesium 26? 78.7% of the magnesium in the world is magnesium 24. when we're calculating the atomic mass, that's going to be reflected. But let's not get ahead of ourselves. Let's do a little bit of a learning check to make sure you understand isotopes. So please pause it here, give this one a shot, and then look at the answers. Which of the pairs below are isotopes of the same element? If it's the same element, then we would expect them to have the same atomic number. So which pair has the same atomic number? That would be B. In which of the pairs below do both atoms have 8 neutrons? To figure out the number of neutrons, you take the mass number and subtract the atomic number, which is the number of protons. 15 minus 8 gives you 7. So obviously, that one can't be it. A can't be it. 12 minus 6 gives us 6 neutrons. So it can't be that one. It's got to be C, but let's make sure. 15 minus 7 gives you 8. 16 minus 8 also gives you 8. So that one is letter C. When you're in a test setting, you'll need to know all of these because you won't get this as an equation, mass number minus atomic number. You simply need to know their definitions and how they're related. Here's some practice for you. I'm not going to fill in the whole chart, but you can fill these in on your own and make sure you understand it. And if you have questions, you can always send me a message. I'll fill in the first one, and then you can fill in the other two. Given the atomic symbols, determine the number of protons, neutrons, and electrons. We know that the atomic number is going to be that bottom number. The mass number is the top number. The atomic number is the same thing as the number of protons. And in a neutral atom, that number should also be the same for the electrons. So the only thing we really have to do any math for is the number of neutrons. Atomic number we fill in as 8. Mass number, 16. Number of protons, 8. We'll come back to the neutrons. And the electrons, 8. So 4 out of 5 answers simply by knowing the definitions and how to read an atomic symbol. For the number of neutrons, you have to take the mass number and subtract the number of protons, or the atomic number. 16 minus 8 gives us 8. You can fill in the other 2 rows just to make sure that you understand the concepts. If you don't understand it or you want to have confirmation of the answers, you can always reach out. We brought up atomic mass. We need to talk about how it's calculated. The atomic mass is the weighted average of all the naturally occurring isotopes of that element. Here we're talking about chlorine. That's our example on this slide. There are 2 naturally occurring isotopes, chlorine 35 and chlorine 37. They each have a percent abundance. Most of the chlorine that you'll find is of the chlorine 35 variety. The number that you see on the periodic table, that's the weighted average. That's the atomic mass, the one with the decimal. And it takes into account what percentage of each element has what isotope. So since this one has 75.76% of the chlorine being of the chlorine 35 variety, the average of the weight is going to lean closer to the mass of chlorine 35. Let's do a sample problem so you can see what this means. Let's say that we have gallium. It's found in lasers that's used in CD players. Okay. In gallium, you have 60.10% gallium-69, and you have the atomic mass of gallium-69. We've got the other percentage abundance for gallium-71 and its atomic mass. What is the atomic mass of gallium? Remember, we have to calculate a weighted average. And a weighted average is different from a regular average. A weighted average takes into account how much you have of each atomic mass in this case, not just the two individual atomic masses. You'll get a very different number if you do one versus the other. What I like to do for these problems is make a table. That way I organize all the information that I have, and if I need to fill in any blanks, I can do that, and then I can calculate my atomic mass. So I've got my isotope, percent abundance, and then I want to express that percent abundance as a fraction. Then I have my atomic mass for each isotope. We've got two isotopes. Gallium-69, we're told that it's got 60.10% abundance. To express this abundance as a fraction, remember percentages are out of 100. So that's the percent abundance expressed as a fraction. The atomic mass we were given, 68.926, and that's an AMU. The second isotope is gallium-71. Its percent abundance from the problem, and we express that as a fraction out of 100. And we're setting this up so that when we go to do our math, it's really easy. So here's our table organizing everything. What you want to do, and I'll show you what you write into your calculator, is you want to take the percent abundance expressed as a fraction and multiply that by the atomic mass. So for the gallium-69, you take the 68.926 and multiply that by 60.10 over 100. That's the first part for gallium-69. We're going to add that to the same thing for gallium-71. You take that 70.925 AMU, multiply by its abundance. Whoops. Make sure you write the correct abundance. Don't be like me. So you'll need to do those two calculations. And you'll end up with the weighted average. So if you want to look at it from our chart, you're multiplying there, you're multiplying here. And then you're going to add these two together. Make sure you practice putting that into your calculator. We'll do some practice problems where you aren't given all of the percent abundances. And you'll have to remember that a percentage is out of 100. So you can always fill it in, just have to do an extra step. That's it for the first part of chapter 4. We'll finish up this chapter in part 2. Make sure that you tune into the live lecture for practice problems and details regarding assignments and exams. Until then, be safe.